Dear student, this is the fourth class on the chapter power series solution of differential equation special functions. And I once again welcome to this class. And in this class, the topics that will be covered are Rodrigue's formula for Legendre polynomials, problems related to Rodrigue's formula, and finally associated Legendre equation. Now come to the points or topics. First, Rodrigue's formula for Legendre polynomials. For Legendre polynomials, the Rodrigue's formula is an important formula, and with this Rodrigue's formula, the Legendre polynomials can be found out. And here, the Rodrigue's formula for the Legendre polynomial Pnx. Pnx is the Legendre polynomial, and Rodrigue's formula for these polynomials is given by 1 by 2 to the power n into n factorial, then d to the power n dxn into x square minus 1 into x square minus 1 to the power n. That is, this is a constant, and then the nth differentiation of x square minus 1 to the power n, this term. And this can be put and which is shown below. That means this function, that is this formula, with this formula, any Legendre polynomials, any order, polynomials of any order can be found out. Now let us try to prove it. Now to do this, we consider that v is taken as x square minus 1 to the power n. So from this relation, it is easily found out. It is easily found out the value of dv by dx. That is the first differentiation of v with respect to x, which is equal to n. First, the derivative of this term with respect to x is first n into x square minus 1 to the power n minus 1 into the differentiation of x square. That means 2x, which is equal to 2nx x square minus 1 to the power n minus 1. Now multiplying this equation or this relation, that is dv by dx is equal to 2nx into x square minus 1 to the power n minus 1 by the term x square minus 1. We get first term is this, so 1 minus x square, or it is x square minus 1. So this term will be, if we multiply this equation or this relation with x square minus 1, this term, then then it turns to x square minus 1 dv by dx, that is equal to 2nx into x square minus 1 is here, and here is x square minus 1 to the power n minus 1. So it will be x square minus 1. So the relation comes is equal to is x square minus 1 dv by dx is equal to 2nx into x square minus 1 to the power n. And from this, one can write, from this relation, one can write x square minus 1 dv by dx is equal to 2n vx, because we have taken v is equal to x square minus 1 to the power n. So this can be written as 2n v into x. I write this equation as equation number 2, and this equation as equation number 1. So now differentiating equation 2, that means this equation with respect to x, 2n plus 1 times with respect to x using Leibniz theorem. That is, we in this case will use Leibniz theorem to differentiate this equation to n plus 1 terms, and this differentiation will be with respect to x using Leibniz theorem. Then what we will get the first term, write it as x square minus 1 is okay, and then differentiation of this term to n plus 1. So here is first order differentiation is here, and then we have to employ another n plus 1 times differentiation of d, so it will turns to d to the power n plus 2. Here n plus 1 terms we have to do 1 plus 1 n plus 1 terms differentiation, order differentiation, and here is the first order differentiation. So total there will be n plus 2 order differentiation. So d2 n plus 2 by dxn plus 2 into v, and you can see the Leibniz theorem by any books or on the website, and the formula that will come, that if you differentiate this type of variable or this type of function, then the first term will come here, and then the differentiation of this term to this n plus 1 times, and I have written this, and then the term formula comes that here will be n plus 1 into n plus 1 c1, n plus 1 c1, and then first order differentiation of this term, that is 2x here, and then the differentiation of v will be what you did in this case, one term later, one order smaller or lesser than this term. That is, in this case, the differentiation will be n plus 2 minus 1 or dxn plus 2 minus 1. That means dn plus 1 by dx1. Okay, that means in this case the differentiation will be one order less than this. That means dn plus 1 order differentiation of d. So according to Leibniz theorem, the second term will be first, right? According to the Leibniz theorem, the constant will come here as n plus 1 c1, then differentiate it for the first time or first order, that is 2x, and then the differentiation of v one order less than that of this term, this differentiation. That means d to the power n plus 1 by dx to the power n plus 1 into v, and then plus the constant term will come n plus 1 c2. This is for the first order, this is for the first term, and this is for the second term. So the second term will come as n plus 1 c2, then differentiate this for twice. That means it will be 2, only 2, and then the differentiation of v, that v will be one order less than this term. That means d to the power n by dx and v. So I hope that this is understandable to you, and this will goes until a constant is come from this term. So here 2 is a constant, this term comes here, arises here, so we will stop here the differentiation. So what is the differentiation of this term with respect to x to n plus 1 terms using Leibniz theorem? First, take this term as constant and differentiate this term to n plus 1 times. So it is there d to the power n plus 2 by dx n plus 2v. Then take a constant which is n this term n plus 1 c1, and differentiate this for the first time, so 2x, and then differentiate this v one order less than this term, that means d to the power n plus 1 dx on d, and then plus another constant will come for the third term, which is n plus 1 c2, then differentiate this term for twice, that is 2, and then the differentiation of v one order less than that of the previous term, that means d to the power n by dx and v. And similarly, if we differentiate this to n plus 1 times, according to Leibniz theorem, we will follow what we did in this in these three terms. So first, this 2n is a constant which is taken here, and then there are two terms remaining here, which are v into x. So you take v as a constant as taken in case of this term, in case of this term. So here x is a constant term, and differentiate v to n plus 1 times. That means dn plus 1 by dx and v. Then the constant which will come is nothing but n plus 1 c1. Then differentiate this x for the first time. That means it will give you 1, and then differentiate this v to one order less than that for the previous term. That means d to the power n by dx and into v, as the constant one has arised here. So we will stop here the differentiation. So after differentiation of this equation with respect to x or to n plus 1 times using Legendre, we will get we have got these terms. Now to simplify the above equation, that means this equation. So here we write x square minus 1 d to the power n plus 1 n plus 2 v dx n plus 2, then plus 2x is a 2x is taken here. So this is the x term, the term related to x, and here is the term which consists of x term. So we take as 2x is a constant term. So here the remaining part is n plus 1 c1, and minus from this I have taken this term to the left hand side. So here the remaining part of this term will be minus of n, and this whole term will be multiplied by d to the power n plus 1 dx1 into v, dn plus 1 dx1 d, and then plus from the remaining part, terms, that means this term and this term. So here you see that from this term, if you take 2 is a constant term, so the remaining part will be nc1, and also we take dnv dx and d is a constant, and it is a common term from this term and from this term. So 2 into dnv dxn, it will be dxn. Okay, it will be mistakenly written as 2, so it will be n. So 2 into dnv dxn, and the term which will be in the bracket are nc1 nc2 n plus 1 c2, which will come from the term and it is also here. So plus, here is a plus sign. So 2 into dn dxn, this is taken as common term, and remaining part is n plus 1 c2. c2 is here, and we are shifting this term to the left hand side. So from here n plus 1 c1 with a constant n. Here is n. So n into n plus 1 c1. So next, x square minus 1 d to the power n d to the power n plus 2 dx n plus 2 v. This is the first term. Okay, then plus 2x. This is the 2x is here, and just simplify this, and you know that n plus 1 c1 is equal to n plus 1 factorial by 1 factorial into n plus 1 minus 1 factorial, which is written here, and you know that n plus 1 factorial can be written as n plus 1 into n factorial, because n factorial n is equal to n into n minus 1 factorial, and in here it will be actually n plus 1 minus, that means n factorial. So n factorial and n factorial will cancel each other, and then minus n is here, dn plus 1 v by dxn, plus here 2 is here, this 2 is here, and if you simplify this, you will have n plus 1 factorial, and this n plus 1 factorial can be written as n plus 1 into the next term is n, and the further next term is n minus 1 factorial, and here 2 factorial into n plus 1 minus 2, it is written as factorial. So it is actually n minus 1 factorial, and this n minus 1 factorial and this n minus 1 factorial will cancel each other, and minus this n is here, and n plus 1 factorial will be in the numerator. So n plus 1, and you can write it as n plus 1 into n factorial, and here will be 1 factorial into n plus 1 minus 1 factorial, that means it is n factorial. So n is n factorial and this n factorial will cancel each other, dn v dxn, that is equal to 0, and the next term that will be, so now we get x square minus 1 dn plus 2 v dxn plus 2 plus 2x is here, and after being simplification, you see here that n plus 1 term is remaining here, and here is n, so n and n will cancel out, and only you will have 2x dn plus 1 v by dxn, and the final term is plus 2 is here, and you obtain from this term is n plus 1 by 2 is here minus n into, oh yeah, it is n into n plus 1 by 2 minus n into n plus 1. So after simplification, so it is written here n into n plus 1 by 2 minus n into n plus 1 dnb by dx, and that is equal to 0. Now only thing is to do to simplify only this term. The remaining term will, the first two term will be as usual. So it is written here, and then from here you can simplify it, and this will give you n into n plus 1 by 2 minus n into n plus 1. So it the subtraction will be minus n into n plus 1 by 2, and that two and that two will cancel each other, and you will get n into n plus minus n into n plus 1 dn v dx, and that is equal to 0. So 1 minus x square dn plus 2 v dx n plus 2 minus 2x dn plus 1 dn dx n plus 1 v plus n into n plus 1 plus n into n plus 1, because we have changed sign here. So from this you can write 1 minus x square. So this will be a negative sign, this, and this sign will be positive. So n into n plus 1 dn v dx, and that is equal to 0. And write it as equation 3. Now if we substitute d to the power n dn d dxn as is equal to y, then what you will get? You will get, for the first term is 1 minus x square d2y by dx square minus 2x dy by dx plus n into n plus 1 into y, that is equal to 0, which is the familiar Legendre equation. So therefore y is equal to, we substitute here y is equal to dn b by dxn. So this should be a solution of Legendre equation, because this y is equal to dn v dxn satisfies the Legendre differential equation. So y is equal to dn v by dxn is a solution of Legendre equation, and you also know that y is equal to pnx is another solution, is also a solution of Legendre differential equation. So from these two you can write that pnx is equal to c is a constant into dnb dxn, where because these two are independent solutions, so you can write one of them as, that means pnx is equal to c is as a constant into dnb by dxn, where c is a constant. Now you know that v is equal to, you have taken as v is equal to x square minus 1 to the power n, and it can be written as x plus 1 to the power n into x minus 1 to the power n. And if you differentiate this term to n with respect to x to n times, then you will have dnv by dxn, that is equal to, for the first term you take x plus 1, for this is x plus 1 as constant, so x plus 1 to the power n dn dxn x minus 1 to the power n. That means you will have to perform the nth order differentiation of x minus 1 to the power n terms, and then what will come, then the next term will be nc1. nc1, remember here that you are using here the Leibniz theorem. So the constant term next will come in nc1, then differentiate this term for the first time, that means n into x plus 1 to the n minus 1, then differentiate this term one order lesser than this order, so that will be n dn minus 1 by dx minus 1 into x minus 1 to the power n, and in this way the other terms will come, and the last final term will be x minus 1 to the power n dn xn x plus 1 to the power n. So here you see that this term dn by dxn x minus 1 term, that means this term you have to perform the differentiation of x minus 1 to the power n for n times. So what we will get for the first differentiation, you will have n into x minus 1 to the power n minus 1, and the remaining differentiation which we have to perform is d to the power n minus 1 by dxn. So if you differentiate for the second times, then the constant term will be n was for the first case, and then n minus 1 will be the second case, and there will be remaining differentiation which are d to the power n minus 2 by dxn minus 2 x minus 1 to the power n minus 1. So then you will get for the after third differentiation n into n minus 1, n minus 2, and then so on. If you ultimately differentiate for the n times, then you will get the constant 1. So the differentiation of x minus 1 to the power n for the n times you will get the result as n into n minus 1, n minus 2, etc. to 1. That means it is n factorial, nothing but n factorial. And here it is written, since for the last term dn dxn 1 minus n to the power n is nothing but dx of x minus 1 when n for the last term, and that will give you 1. So I have written here for the 1 as the last term. So you get this differentiation as a factorial n. Now first term, that means this term x plus 1 to the power n dxn x minus dxn dn by dxn 1 x minus 1 to the power n, that will give you the result x plus 1 to the power n into n factorial. And for the second term, what is the second term? Second term is the nc1 n into x plus 1 to the power n minus 1 dn minus 1 dxn minus 1 into x minus 1 to the power n. So you are differentiating these x minus 1 terms minus 1 to the power n to n minus 1 times. See here, in this case we have differentiated this term to n times, and the last term was 1. And if you differentiate one order less than this, then the final term will be x minus 1, because this is the last term, this is the last derivative of this series. So the one order less, that means this order differentiation will give you this term x minus 1 term. I hope that you understand this. So the last term will be x minus 1, and this x minus 1 will be multiplied to all the, and I see from this relation that this x minus 1 here also, that see that this term also consists of x minus 1 term. So this x minus 1 term will be associated with all other terms except the first term. Okay, except the first term. So if you so here it is written clearly that this term will be differentiated till n minus 1 term, and finally there will be x minus 1 multiplication with the resultant. That is, in each term of these there will be a factor n minus 1. Now if you suppose, or if you take x as is equal to 1, so one term, that is, if you use x is equal to 1, then x minus 1 will vanish, and then this will give you 0, equal to 0. So except the first term, all other terms will vanish, and then dnb dxn will give you the result x plus 1 to the power n into n factorial, because in this case only the first term will be there, and all other terms will vanish. So dnb dxn is equal to 2 to the power n factorial, and you know that dnb dxn is equal to you have written is as y, and also you know that pn x, that is the Legendre polynomial, that is equal to c, a constant, into dnv dxn. So c into dnv dxn, or in case of x is equal to 1, you can write pn here you write 1, that is equal to you also know that in the recurrence relations, or in case of you previously you know that in case of Legendre polynomials, that the nth order Legendre polynomial for x is equal to 1 is equal to 1. So pn1 as we used x is equal to 1, so pn1 is equal to 1, that is equal to c into, you just substitute, or you use the value of dn v by dx, and that means 2 to the power n into n factorial. So from this you can obtain c as is equal to 1 by 2 to the power n factorial. So finally, what you want, find, that is Pnx is equal to 1 by 2 to the power n factorial dn dxn. So the Legendre polynomial can finally be written as Pnx is equal to 1 by 2n n factorial dn dxn. You just write here the value of d, that is x square minus 1. You have taken as b is equal to x square minus 1. So finally you get Pnx is equal to 1 by 2 to the power n factorial dn dxn x square minus 1 to the power n. And this is very important, and see here that you previously, or for the starting of this Rodrigue's formula, you have considered that Pnx, the Legendre polynomial is equal to this, which has been proved in this. So it is proved that the Legendre polynomial can be given as this, in this way, and this is also called the differential expression for Pn or Legendre polynomials. Now here we wish to find some Legendre polynomials in accordance with Rodrigue's formula, and for the first case, that is here, we wish to find out P0x, that is the Legendre polynomial for 0th order, and that will be is equal to, you know that the Rodrigue's formula was 1 by 2 to the power n into n factorial, and then into dn dxn x square minus 1 to the power n. Since in this case n is equal to 0, so this term will be there will be no differentiation, and also since x is equal to 1, so that will there will be, this term will give you 1, and first term, that is 1 by 2 to the power n means 0, and 0 factorial, that will give you 1. So when using n is equal to 0 in this relation, you can find out the Legendre polynomial for the 0th order. That means P0x. So you get here this, and no, here you see that if you use n is equal to 0, so it will be n is equal to 0, so no differentiation is here. That means you get it is equal to 1. Now for the second term, that is if you use n is equal to 1, then what we will get P1x, that is equal to 2 to the power n. Using Rodrigue's formula, it was 2 to the power n, so 2 to the power 1, then n factorial, 1 factorial, dn dxn, so here n is equal to 1 here, so dtx, and it is, and the term here is x square minus 1 to the power n, that means x square minus 1. So that is equal to 1 by 2 comes from here, and if you differentiate this, you will get 2x, so it is equal to x. So P1x is equal to x. Now P2x. So using Rodrigue's formula, P2x is equal to 1 by 2 square into 2 factorial d2 by dx square x square minus 1 whole square, that is equal to 1 8 come here, and dtx of first differentiation of this is equal to 2 into x square minus 1, and then 2x from here, from this term. So that is equal to 4 by 8 dtx of, if you just simplify, you will get x cube minus x, and so P2x is equal to, now differentiate this term, that will give you half x3 x square minus 1, and now P3x, that is equal to, using Rodrigue's formula, 1 by 2 cube into 3 factorial d cube by dx cube x square minus 1 whole cube. So that will give you, this term will give you, this first term will 8, and this term will give you 6, and d2 by first time differentiation is there, so it will give you 3 into x square minus 1 whole square into 2x with d2 by d2 dx square. Now it will give you, and this 3 2 will cancel out with 6, so 180 d2 dx square into just simplify this or expand this in formula, that is x equals x to the power 4 minus 2x square plus 1 into x. That is equal to 18 d2 dx square, and you get from this line that x cube x to the 5 minus 2x cube plus x. Now it will give you 18 d dx of differentiate this. So this will give you 5x to the power 4 minus 6x square plus 1. So that is equal to 18, and differentiate this, and it will give you 20x cube minus 12x. So finally you get that if you take 4 as a common term from these two terms, so 18 into 4, 5x cube from here, the remaining part is 5x cube minus 3x from here. So it will finally give half 5x cube minus 3x. So you can also find other Legendre polynomials, other order Legendre polynomials of other different orders using n is equal to 4, 5, 6, etc. and subsequently differentiate the term x square minus 1 to the power n. Now here we are trying to plot the different Legendre polynomials. So you can see from the first Legendre polynomial, that is p0 p0x, the value of p0x is equal to 1, and here we plot x is in this axis and pn x according to the y axis. So in case of, and if right here this is minus half, this point is minus half, this is 0 the origin, and this is minus 1, and this is plus half, this point as, and this point as plus 1, and you write this point is as plus 1, and this is equal to minus half, and this is equal to, this point is minus 1. So in case of p0x, you have seen that p0x has the value 1. So if you plot it, it will be straight line in this way. So this line comes from p0. Next, p1x. P1x was, what was p1x? P1x was x. So p1x is x. So if you use x is half, x is as half, then p1x will be half. So it is here, it will be here, this is half point half, so it will be half. And if you use x as 1, then p1x will be 1, that is here. In the similar fashion, when x is minus half, so it is minus half, and it is minus half, so p1x will be at that point, and for x is equal to minus 1, p1x will be here, this is minus 1. So this is minus 1. So if you join this, it will be a straight line in going through the origin, and it will be passing through the origin, and this straight line will be here in this way, and it will cross the 0 and touch this. It is mistakenly given here. If you use scale, then it will go through this point. So the straight line will be in this direction, from starting from here, it will go through the origin and reach to this point. Okay, and then for p2x, you know p2x is equal to, finally comes as half 3x square minus 1. So if you use x is equal to 0, so what you will get, x is equal to 0 means half, p2x will be half. So from this relation, so half is, so here x is 0, here x is 0, and not half but minus half, because the second term was minus 1. So at x equal to 0, it is here p2x is minus half. And if you use x is equal to 1, then from this relation, what you will have? You will have 3 into 1 minus 1. That means 2 minus 1. That means it will 3 minus 1. That it will give 2, and this 2 and this 2 will cancel. That will be that the finally p2 1. p2 for x equal to 1 will be 1. So here it is for x equal to 1, p2 1 will be 1, that is here. And similarly, for x equal to minus 1, P2 will be minus here. Okay, so it will also be 1 because 3x square term is there, x square term is there. So for x is equal to plus 1 or minus 1, P2 will be plus 1. So just uh, just connect these points. So you will get is at parabola. Now hyperbola, parabola, sorry, it will give you parabola. Next, for P3, you have P3 is equal to half 5x cube minus 3x. So for x is equal to 0, x is equal to 0, if you use x equal to 0, it will give you 0. So for x equal to 0, P3 equal to 0, it is, this point is here. Now for x is equal to 1, I am writing 1 here. So 1, and it will give you 5 and then minus 3, that means 2, and this 2 will cancel out, and finally you will have P3 for x equal to 1 as 1. So it is written here, it is 1, so it is written here 1 is there. Okay, 1 is there. And now for x is equal to minus 1, so you will have minus 5 from here and plus 3 from here, and resultant will give minus 1. So it is written here minus 1 is there. For minus 1 it is minus 1. And if you use as x is equal to half, x is equal to half, then actually you will obtain P2. It is your homework. P3 will be here. For the minus half it is minus half, and for plus half it is also minus half. Okay, and you will connect this, you will have like this. This is for P3. So if you, the general term of Pnx, that is the Legendre polynomial, according to Rodrigue's formula, which is written here, this, that which is written here, Pnx is equal to this, and as you calculated different types of Legendre polynomials using Rodrigue's formula, the final term, or in general term, Pnx can be written as r equal to 0 to n minus 1 to the power r, 2n minus 2r factorial by 2 to the power n r factorial, n minus r factorial, n minus 2r factorial, x to the power n minus 2r. You can substitute different values of, or use different values of r in this relation, and then you will get all the terms P1, P2, P3 as calculated in earlier in the previous sections, previously. So that will match using this relation. The different value of P1, P2, P3 or P0 will match as those calculated here and here. So you have to check it, and this is also your homework. Now here is a problem which is given here: express 5x cubed minus x plus 2 in terms of Legendre polynomials, and you know that using Rodrigue's formula, was what is P and x is equal to 1 by 2 to the power n into n factorial dn dxn x square minus 1 to the power n. Now using Rodrigue's formula, you also know that P0x is equal to 1, which is already calculated, and P1x is equal to x, P2x is equal to half 3x square minus 1, and P2, and P3x is equal to half 5x cubed minus 3x. All of these terms have already been calculated. So from the last term, you can write 5x cubed is equal to 2p cubed plus 3x. Now the function given you is fx is equal to 5x cubed minus x plus 2, and it can be written as 5x cubed is from here 2p3 plus 3x, as 5x cubed is equal to this, and then minus x plus 2, and this will give you actually 2p cubed plus 2x plus, as 2 into 1 is p0x, so it is 2p0x, and finally x is equal to also p1x also, so it will finally give 2p cubed x plus 2p1x plus 2p0x. So actually so finally 5x cubed minus x plus 2, this term can be written as 2p cubed x, 2p3x, actually 2p3x plus 2p1x plus 2p0x. So all these terms is converted into the Legendre polynomials. So next, here is also another problem, which is we have to prove that minus 1 to plus 1 Pn x mod whole square dx is equal to 2 by 2n plus 1, where n is equal to 0, 1, 2, etc. And to do this, we have to recall the orthogonality property of Legendre polynomials, which was minus 1 to plus 1 integration minus 1 to plus 1 pmx dx, that is equal to 0, where pn and pm are the Legendre polynomials of nth and mth order respectively, and in this case m not is m not is equal to n. Now, however, if you consider that n and m are equal, that is m is equal to n, then from this relation you have minus 1 to plus 1 integration minus 1 to plus 1 pn square. You can also write it as pn mod whole square, that into dx is equal to 0. So from here you also know that the generating function of Legendre polynomial, that is 1 minus 2xt plus t square to the minus half, that was sum over n is equal to 0 to infinity t to the power n p n x, and from these if you expand these, you will have 1 plus t into pn1x plus t square p2x plus other terms at pnx, etc. So just square this term, squaring both sides, this relation. So you will have n equal to 0 to infinity t to the power n pnx square, that is equal to this term will multiply with another this term. So it is written here this into this, and that is equal to, if you square this, you will have 1 minus 2xt plus t square to the power minus 1. Now integrating both sides, what will have, you will have minus 1 to plus 1 t to the power 2n pn square x dx, that is equal to minus 1 to plus 1 integration dx by 1 minus 2xt plus t square. And remember that from this relation minus 1 to plus 1 pn square x, it would be better if you use mod pnx square, okay, and pn square pnx square dx, that is nothing but the coefficient of t to the power 2n of this term. Since it is equal to this, so t to the power n term is also present here, and if you compare, then you will have minus 1 to plus 1 integration minus 1 to plus 1 pn mod whole square dx is equal to coefficient of this term, coefficient of t to the power n in this term also. So here, just here, so this is here also written coefficient of t to the power n in this, and now this integration, I to simplify this, right here minus 1 to plus 1 dx 1 minus 2xt t square, that is equal to you can write just see here, see below here, d of 1 minus 2xt plus t square is calculated, and it will give you minus 2t dx. So from here dx can be written as 1 by minus 2t d of 1 minus 2xt plus t square, and just substitute the value of dx in the in where substitute dx by 1 d of 1 minus 2xt t square here. So this will give 1 minus 2t minus 1 to plus 1 d of 1 minus 2xt t square by 1 minus 2xt plus t square. So after differentiation, integration, you will have 1 minus 2t is here, and d of this, so if you take it as z, dz is here and z is here, so dz by z is equal to log z. So that is written here, log 1 minus 2xt plus t square minus 1 to plus 1, and this will give you, for plus 1 it is 1 minus 2t plus t square, that is 1 minus t whole square, and minus 1 will give you 1 plus 2xt plus t square, that is 1 plus t whole square. So this term will give you 1 minus 2t log the natural log 1 minus t by 1 plus t whole square, and from this we have minus 1 by 2t into this 2 will come here, 2 log 1 minus t 1 plus t. So finally you get 1 by t, and if you can write this term as log 1 minus of 1, you can write log 1 minus t by 1 plus t as minus log 1 plus t by 1 minus t. That is written here. And the additional minus sign coming from here, and these will cancel it. So 1 by t ln log 1 plus t by 1 minus t. So this is also can be written as 1 by t log 1 plus t minus log 1 minus t. And now just expand this term log 1 plus t and log 1 minus t. If you expand log 1 plus t, then the terms which will arise are t minus t square by 2 plus t cube by 3 plus all other terms. And you can see the series expansion of log x, and that will be in this manner. And then log n minus t will give you, this is the minus, this minus n minus t square by 2 minus t cube by 3 plus etc. So after simplification you will have 1 by t, and t is here, another t is from this term, so 2 into t, and then pass this t square and this t square will this term and this term will cancel out, and this is t3 by here, t3 by 3, and minus this minus and this minus will be a positive sign, and t cube by 3 is also here, so there will be 2t cube by 3. So as 2 is taken as common term, so it will be t plus t cube by 3 plus all other terms. That is equal to, now if you take t as common terms from all other terms, so this t, the common t, and this t will cancel, so finally we will get 2 into 1 plus t square by 3 plus all other terms, and the final term will be, since it is written as t square, so t to the 2n for the nth term, and here 3 is actually where is equal to 2n plus 1, and there will be 2n plus 1. So I hope that you will understand that 1 plus t square by 3 plus all other terms. So in this case n is equal to 1. If you take n is equal to 1, so t square, that means 2 into n. So it is written as 2 into n, and 3 is, as in case n is equal to 1, so 2n plus 1, so the final term will be t to the n by 2n plus 1. So minus 1 to plus 1 integration minus 1 to plus 1 pn square x dx, it is better to write mod pn x whole square, that is equal to 2 by 2n plus 1, or n is equal to, it is proved. So now we come to the last topic of this chapter, which is associated Legendre equation. You know that the Legendre equation is given by 1 minus x square d2x by dx square minus 2x dy by dx, and then plus n into n plus 1 into y. But the Legendre associated equation is written as the two terms, first two term as usual, and then plus n into n plus 1 minus m square by 1 minus x square into y, that is equal to 0. I write it as equation 1. This is the associated Legendre equation, and this equation differs from the familiar Legendre equation formed by the presence of the last term, that means minus m square by 1 minus x square. So you can use Gauss's method to solve this equation, but we are not here to perform that. But the solution of this equation, that means that the associated Legendre equation is given by is given by y is equal to 1 minus x square m by 2 dm dxm pnx, where pnx is the Legendre polynomial, and since it is a relation, it is the solution of this equation, and here we are to prove it. And to prove it, we just recall that Legendre differential equation, which is written here, is equal to 0, and we just differentiate this Legendre differential equation to m times with respect to x, and using Leibniz theorem, then what we will get, since you already understand the method to differentiate using Leibniz theorem, so in this case it will not very difficult to understand the differentiation of this Legendre equation with respect to x by using Leibniz theorem. So first of all, for the first term, you have to take 1 minus x square as constant, and then differentiate y to this term to m times. So already second order differentiation is there, and you are now have to perform n times differentiation. So total differentiation will be n plus 2 term order, So it will be m plus 2, yeah, m plus 2 dm plus 2 dxm plus 2y, and then the constant term which will come here, since you are doing m times differentiation, so mc1 is there, then differentiate this term for the first time, so it will give you minus 2x. So then differentiate y one order less than this term, so it will be m plus 1 y by dxm. Then the common term, then the constant term will come as m, since mc1 is here, so next term will be mc2. It is written as mc2, and then differentiate this term for the second time, or second order differentiation. Take the second order differentiation of this term, which will give you minus 2. So since the constant term comes here, so there will be no other differentiation of this term, so we'll stop here for the first term. So this is mc2 minus 2, and differentiation of y here will be one order less than that of the previous term, that means dmy by dxm. Now for the second term, minus 2x dy by dx. So here minus 2x is constant, and then differentiate these 2m times, so it will give you dm plus 1y by dx m plus 1. Then this minus time then it is take, then minus term will come here, minus sign will come here, minus, and constant will come here as mc1. So it is mc1, then differentiate these, then and it will give you, 2. It will give you 2. So it will, that means you have to differentiate for the second time of 2x, for the first time. So first order differentiation of 2x will give you 2. So it is written as 2, and into the differentiation one order less than that will be the previous term, so it will be dmy dxm, and plus n into n plus 1, and you are doing at m time differentiation of y, so it will dmy dxm. Now the following some lines are to simplify this equation. So here write this term as well, and this from this minus 2x is here, and just expand this, so it will give you m factorial, and that is m factorial means m into m minus 1 factorial. You can write it as this, and in the denominator we will have 1 factorial into m minus 1 factorial, and this m minus 1 factorial and this m minus 1 factorial will cancel each other, and then dm plus 1y by dmx dxm plus 1, then minus this here from from this term. So this minus will give you a minus sign here, so this is 2, and if you expand this, it will be m factorial by 2 factorial into m minus 2 factorial, and m factorial here can be written as m into m minus 1 into m minus 2 factorial, and in the denominator the term remaining is 2 factorial into 1 m minus 2 factorial, and then dmy dxm. So this m minus 2 factorial and this m minus 2 factorial will cancel each other, and after that from this term it is 2x dm x dm plus 1 dxm plus 1y. It is as usual, and then this term can also be written as minus 2 into m minus 1 factorial by 1 factorial into m minus 1 factorial dmy dxm plus n plus 1 dmy, the last term here, nothing is changed here. So here this term is written as usual, and from this you will have 2x, and m is here, m is from here, so it will give you 2x m dm plus 1 dxm y, and from here you have m into m minus 1, so it is written minus m into m minus 1 dmy by dxm. It is also here. Now from this term is written as it was, and also from this term you have 2m, so it is minus 2m dmy dxm, and the last term is as it was. So we get finally this term. Now just simplify, we have to simplify this relation. So 1 minus x squared dm plus 2y dx n plus 2, it is as it was, it is as usual, what is written here, and this is written as you see here 2xm dn plus 1 dx. This from this term and from this term. Okay, you take 2x, so this term and this term can be written as 2x m plus 1 dm plus 1 dx m plus 1 y, and then from the term, this term are from this term and this term, that is the terms consisting of dmy dxn. So you write n into n plus 1 here, and from here minus of am into m minus 1, and also another term is here, also here minus 2m is here, dmy dxn is equal to 0. Now nothing is to do for the first two terms, that is this term and this term, which are written here, this term and this term. Only just simplify these and you will get this in this manner, and after that these two terms remains the same, and you can simplify these as n minus m, this n and this m. Oh, and this is plus m and this is minus m, so here will be minus m. So n minus m is written here, and from this term and this term, n plus 1 into n minus 1 n minus m is equal, and dmy and dx is equal to 0. After that, first two terms remains the same, and from here you will have n minus m into, it is a constant term, so the remaining part is n plus m, and from here another 1. So n minus m, n plus m plus 1 dmy dxm, that is equal to 0. Now writing dmy dxm is equal to u, and if we write this u as is equal to this, then from this equation you can write 1 minus x squared d2u by dx squared minus 2x n plus 1 du by dx plus n into n minus 1 m into n plus this, and to y is equal to 0. I write this as equation 3. Now since Pnx, that is Pnx is a solution of Legendre equation, so we can write u as equal to, since u is taken as d to the power dmy by dxm, and that is equal to dm dxm, since y is equal to Pnx, so Pnx is right written here, and this will be a solution of equation 3. Okay, now from equation 2, that is now from equation 2 we have equation 2 is y is equal to equation 2 is where the equation 2 was written in initially for the in the first part, that is equation 2 is written here, just go, yeah, it is here, y is equal to 1 minus x square to the power m by 2 dm dxm pnx is this, and since you already have taken as dm dxm pnx is equal to u, so you will have u is equal to 1 minus x square to the power m by 2 into u, that is written here. See here, that is written, u is equal to 1 minus x square, so y is equal to u into 1 minus x square to the power m by 2, and from this you can write u is equal to 1 minus x square to the power minus m by 2 into y. Now to satisfy this relation, this equation, we have to substitute here the values of d2y dx square and du by dx and u also in this relation, and if this relation, from this relation we finally get the Legendre polynomial, then we can easily conclude that y is equal to y that is given by equation 2 is the solution of Legendre polynomial equation, associated Legendre polynomial equation. So now here we are trying, we are here doing the to find out the values of dx du dx, that is equal to what you have u is equal to 1 minus x squared to the minus m by 2 into y, so du by dx, so du by dx is equal to 1 minus x to the power m, it is a constant to the power minus m by 2, if you take it as a constant term, so dy by dx, and then you have to differentiate this term, so in that case y is constant, so y is written here, and differentiation of this term is equal to minus m by 2 1 minus x squared to the power, you can write in this manner, m plus 2, actually m by 2 minus 1, that can be written as of m plus 2 by 2, and then differentiate this term, that means minus 2 is there, So you get dy by dx 1 minus x square to the minus m by 2 dy by dx plus m is there and x is there, so mx with the plus sign 1 minus x square to the power minus m plus 2 by 2 into y, and also d2 u by dx square, that is equal to, you have to differentiate this term. So for first term this, you take 1 minus x square to the power m by 2 is constant, and then differentiate this d2y by dx square. Then for the term, the first term, so that is equal to minus this power minus m by 2 into 1 minus x square, as that calculated in this case. So it will be minus m by 2 1 minus x square to the power minus m by 2 by 2 into minus 2x into dy by dx is constant here. And then for this term, if x is differentiated in the first case, so it will give you m into 1 minus x square minus of m minus m, since it is written, it is the power is there minus of m plus 2 by 2, so it is written here and into y. So then if you wish to differentiate y, so the term that will be here constant here are mx into 1 minus x square to the power minus m plus 2 by 2 into dy by dx, and finally for differentiation of this term, so right here the constant term, so right here the constant term as mx and y. Mx and y are the constant terms, so right here mxy. And now to differentiate this, so this will give you minus m plus 2 by 2, that here this minus sign is there, m plus 2 by 2 into 1 minus x square to the power m plus 2 by 2 minus 1, which will give you m plus minus of m plus 4 by 2. And then this will give you this term minus x will give you minus 2x. So this is all. Now to simplify, so first term is as that was written here, and second term here it is minus plus mx 1 minus x square to the power this and dy by dx, and then plus m into 1 minus m into 1 minus x square. This term is written here, this term is written here into y, and from this term is also written here, and the last term, this negative sign and this negative sign will give you a plus sign, positive sign, and it will give you, after doing simplification, this 2 and this 2 will cancel out, and this will give you m into m plus 2 x square 1 minus x square to the power minus m plus 4 by 2 into y. Here is mx. So just I write this in this box. Okay, thus only taken y is constant for the last three terms. Now to substitute these values, that is du, d2u by dx square and du by dx in equation 3. That means in the equation, in this equation, and we then get, and if we substitute the value of du by dx and d2u by dx square in equation 3, that is the equation I once again write, because it was in 2 or 3 pages before. So right here 1 minus square, this is the equation number 3, and you write here, you substitute here the values of du dx and d2u dx square. So it is here 1 minus x square, and then 1 minus x square will multiply all these terms. So that will give you 1 minus x square d2u by dx minus 2x into m plus 1. Here 1 minus x square, and then 1 minus x square to the minus m by 2 d2y by dx square, plus the next term is the next term plus 2mx. So it 1 minus x square to the minus m plus 2 by 2 dy by dx. So it will give you 2x m into 1 minus x square. Just here found here 1 minus x square. So if you write here minus of m plus 2 by 2 minus 1 actually. So m plus 2 minus 2 by 2 dy by dx, plus the next term is 1 m into 1 minus x square to the power minus m plus 2 minus 2, as it was done in case of in this case. So into y, then m into m plus 2 x square or minus x square to the minus m plus 4, and then minus 2 by 2 into y, and then minus 2x m plus 1 for the second term. For this term, you are here to substitute dy by dx. So minus 2x m plus 1 into 1 minus x square to the power m minus m by 2 dy by dx plus mx 1 minus x square minus m by 2 into y plus the last term 1 minus x square to the power minus m by 2 n square minus m plus n minus m into y is equal to 0. Just substitute the values, these values d2 y d2 u by dx square and du by dx in this equation. All the steps are given here, so just follow it and you will understand. After simplification, here is the the simplification is written here, given here, and just you follow. I hope you will understand, and finally you will get this 1 minus x square. Just follow, just practice it and just follow, and there will be no difficulty to understand this. But here I am here to simplify the last term only. The first two term will obtain as this, and last term is n into n plus 1 minus m square plus m into n plus 2 x square by 1 minus x square minus then minus 2m into m plus 1 x square by 1 minus x square into y is equal to 0. Just simplify these three terms, this 4, 1, 2, 3 and 4 terms. So here 1 minus x square and then just 1 minus x square should be multiplied with this. So this is taken as n into n plus 1 is taken separately here, and from this 1, 2 and 3 terms. So m square should be multiplied here, no negation is given here, so multiply this 1 minus x square, so it is done here, and then this term is written here, and this term also is written here. After doing simplification, this is very easier, and you will finally get n into n plus 1 minus m by 1 minus x square into y. Thus, from equation I have written, this equation is as equation 6. So substitute the value of the last term in equation 6. This is that will give you 1 minus x square due to y by dx square minus 2x dy by dx plus n into n plus 1 minus m by 1 minus x square into y, that is equal to 0. So we finally get the associated Legendre equation. So y is equal to 1 minus x square to the power m into u, that is equal to 1 minus x square into the power m by 2 into dm dxm dnx is solution of the associated Legendre equation, because using this we finally obtain this equation. So from this we can conclude that y is equal to this, that is 1 minus x square to the power m by 2 dm dxm dnx is the solution of the associated Legendre equation. And so finally, once again we write the Legendre polynomials for the associated Legendre equation, and it is denoted as p and m. So from this relation, since this is the associated Legendre equation, and if you solve it, then the solution, that is p, that is the solution, then the solution will give you this, and you take this as the Legendre polynomial of the associated Legendre, polynomials of the Legendre associated, this whole term, because we know that the solution of Legendre equation is known as the Legendre polynomial. So as it is the associated Legendre equation, the solution of this will give you the associated Legendre polynomials, which is denoted by Pn function of x, and so Pn function of x is equal to this. Now, as in case of Legendre polynomials, different polynomials was calculated. Here we are intending to calculate the different order associated Legendre polynomials. And so for the first case, here is the first Legendre accelerated in the polynomial is here. P11 x is equal to y n is equal to 1 in this relation. So it will give you 1 minus x square to the power half dx of P1x. P1x. Okay, that is equal to 1 minus x square to the power half dx of, and this P1x is nothing but the Legendre polynomial. So P1x, you know that P1x is equal to x. P1x is equal to x. So you write here dd x of x, and this will give you P11x is equal to 1 minus x square to the power half. Then the second order, if you wish to find out P21, that is the second P21. So it will give you, that is 1 minus x to the power half dtx of. You know that P2x here, in this case the formula will be 1 minus x square to the power half dtx of P2x here will be. So P2x is the second order Legendre polynomials, that is equal to half 3x square minus 1. So it is written that P2x is equal to this. So after simplification, you will get 3 into 1 minus x square to the power half into x. So P21 is equal to this. And now P22, that is P22x, that is equal to, it is also calculated here. And then P31. So P31 is 1 minus x square to the power half dtx of P3. P3, you know that the third order polynomial, Legendre polynomial, is equal to half into P 5x minus 3x, and that is, after simplification, all the steps are given here. Just follow it, and finally we will have P31x is equal to 3 by 2 1 minus x square half 5x square minus 1. And in this way, P32 and P33, all these terms are calculated, and the entire calculation are shown here. So in this way, we can calculate different order of associated Legendre polynomials using this relation. So this is the end of this lecture, and dear students, you have to practice all the calculations, and as more as you practice, the whole content will be clear to you, will be easy to understand for you. So this is the end of this lesson, and hope you understand this lecture.